Question 1 in the book is about an ion of plutonium. Now I can't really give hints on how to answer this without giving the answer, so I'm not going to do the one about plutonium. What I'm going to do instead is I'm going to show you how to do a question that's almost identical, except this one's about lead. But the method's exactly the same. So the first thing it asks, nice and easy, how many protons? Well, if we know anything at all about how we write these symbols, we know that the number at the bottom there is the proton number. So in the case of lead, the proton number is 82, so it's 82 protons. Obviously you're going to be doing plutonium, which wasn't 82. How many neutrons? Well, we know the number at the top, in this case 204, that's the total number of protons plus the total number of neutrons. So if 204 is 82 protons and the rest is neutrons, how many neutrons have that got to be? 204, take away 82, 122 neutrons. And then for the number of electrons, well, it does say it's an ion, so we know it's charged. It's got a positive charge, so we know the reason it's got a positive charge is because it's lost electrons. We've got to work out how many electrons has it lost. Now the actual example in the book was a bit easier. I made this one a little bit more difficult. Got a little bit of working out first. If the charge is plus 3.2 times 10 to the minus 19 coulombs, we really ought by this stage to remember what the charge on an electron is. But if we don't remember, it's not a disaster because we can always look on the data sheet. And on the data sheet you'll have the information, the charge on an electron minus 1.6 times 10 to the minus 19 coulombs. And we'll look at the number we've got here. It's still 10 to the minus 19. Instead of 1.6 I put 3.2, which of course is double that. And it's a positive charge because it's electrons that are missing. So if the charge is positive but it's twice as much as the charge on one electron, then it must be because 2 electrons are missing. Now if it was a neutral atom it would have 82 electrons, 2 of them are missing, so therefore it must have 80 electrons. Next part of the question, just the same as the one in the book, except it's talking about lead instead of plutonium. It doesn't answer the question. Explain the meaning of the word isotopes. And when you're answering questions like this, don't beat about the bush. Make sure you put in the precise words that are going to guarantee you get the marks available. So it's very important that isotopes are atoms that have the same number of protons, so you must mention that, the same number of protons, and just as important, you must mention they have different numbers of neutrons. Question 2 says, state the quark composition of a pi plus meson. And that's a nice helpful question because if you couldn't remember that mesons are made up of quarks, the fact that the question asks you to state the quark composition, that more or less tells you, doesn't it? Now if we can't remember much about a pi plus meson, then we need to go and look at our table of properties. So if you're on your data sheet, you look at the one in the book here, and it tells you the properties of quarks. Now hopefully we remember that meson consists of a quark and an antiquark. If we couldn't remember that, and we were looking at this table and just trying to make sense of it, we notice that quarks have got charge and they've got baryon numbers. And we surely know that mesons are not baryons. So we know that it's got to end up with a baryon number that's 0. And since all the quarks have got a baryon number of plus a third, the only way you're going to finish up with a baryon number of 0 is to have something else there that's minus a third, which of course would be the antiquark. So we've got to get a quark and an antiquark, put them together so that the total charge is plus 1, because it was a pi plus meson. So as you look at these, hopefully remember that strangeness isn't going to come into it. So we've got up quarks and down quarks and anti-ups and anti-downs. We've got to mix them together to get a charge of plus 1, and that should be simple enough to do, so I'm not going to show you how to do that. Next part of the question, it gives an equation for 2 protons colliding, and then there's a mystery particle x, and it says we've got to identify what particle x is. So whenever you get equations, you're not expected to have ever met this before, so you're not supposed to remember it from having seen it, you're supposed to be able to work it out. And when particles collide, we know that there are certain rules, certain things that are conserved. So here's the equation. I think, what do we know that's got to be conserved? Well, we know that charge has to be conserved. So let's just check for charge. You got +1 there and +1 there before they collide, and afterwards we've got +1 and we've got +1. So that already balances. So whatever x is must have a charge of 0. What else do we know has to be conserved? Well, we know that baryon number must be conserved. So is a proton a baryon? Yes, so it's baryon number +1. Same for the other proton, baryon number +1. After the collision, we've got a proton, so that's a baryon number of +1. We've got the pi plus, a pion, it's a pi meson. If it's a meson, is it a baryon? No, it isn't, so it's baryon number 0. So now we've got this equation doesn't balance. We've got a baryon number of +2 on the left hand side, got a baryon number of only 1 on the right hand side at the moment. So that tells us that whatever x is needs to have a baryon number of +1. So now we've got two pieces of information. We know it's got to be x must be something that's got 0 charge and is a baryon. And if you go through all the baryons that you know, it won't take long to go through them all before you come across one that's got 0 charge. So that's what x must be. There's no point doing the checking for the third thing. We know that lepton numbers are also conserved, but we know that this is all about baryons and mesons. Leptons don't come into it, so there's no point putting lots of zeros in. We just don't bother with that bit. And once we've worked out what x is, we have to work out its quark composition. It should be quite straightforward. Next part of the question tells you something again that you probably weren't supposed to know beforehand, but it tells you. Pi plus mesons at rest decay into muons, which are always emitted at a certain speed. The equation shows the decay of a pi meson into a positive muon and another particle y. So we've got to identify particle y. And again we do it not by knowing things in advance, but by being able to follow the rules. So we know that you've got things conserved. Baryon number's got to be conserved. But to begin with, it's a pion, a pi meson. Is it a baryon? No, it isn't, so it's got a baryon number of 0. Afterwards it changes into, one of the things is a muon. Is a muon a baryon? No, so baryon number is 0. So we've got 0 for that, 0 baryon number for that. So for the equation to be balanced, can y be a baryon? No, got to be baryon number of 0. Let's look at the charges. We've got a charge of +1 before, a charge of +1 there. So what does the charge of y have to be? Well, it's already balanced, so y must be 0 charge. What's left that we haven't checked? Well, we haven't checked for lepton number. So to begin with, on the left hand side, it's a pi meson. Are mesons leptons? No, so lepton number 0. It changes into a muon. Is a muon a lepton? Well, if you're not sure, you've always got the table to look at. It's in your book. You've got a table of properties of leptons, and the muon is in there in the table. So the muon, negative muon, is a lepton. But our question is about a positive muon. So the positive muon is an anti-lepton. So in our question, we've got, on the right hand side of this equation, we've got an anti-lepton. Left hand side, lepton number 0. Got an anti-lepton there, so what does y have to be for the equation still to balance? That tells you what sort of particle it's got to be. It's got to be a lepton, it's got to have no charge. So you need to choose a suitable lepton that's got no charge. And when you are choosing from the range of leptons. You must remember that if it's neutrinos we're looking at, there's an electron neutrino belongs in reactions where there are electrons. The muon neutrino belongs in reactions where there are muons. So I think I've virtually given the answer there, haven't I?